Hello, this is Mark Armitage coming to you again from the California State University Biology Department Imaging Lab, and we're continuing our discussion and training on the Leica SP5 confocal microscope. Once again, we want to thank the Keck Foundation for their generous support, and of course our videographer Brian and all those who are helping behind the scenes. So thank you for your help. Now we're going to continue with where we left off last time on the LASAF software. By way of review, I want to remind you of the 4 tabs that are across the top left-hand side of the LASAF software screen. The configuration tab allows us to select the lasers and then turn on each laser. We have to apply power to each laser so that they're available to us during live imaging. For the argon laser, we also want to select a power of about 20%. So we click on that and it comes up, well, in this case it's up to 17%, which is fine. Anything at 20% or under. Once the lasers are turned on, we can go to our Acquire tab and begin our experiment. But again, by way of review, I want to point out to you the other 2 tabs that are up here. The Process tab is an important tab with many functions underneath it, which will allow you to do things like your 3D imaging, your maximum projection, your deconvolution, things of that nature. We'll cover these in future sessions. The Quantify tab is also very important for reporting your results in a graph format. And so there are various selections here that you can choose to represent your data in graphic format, in tables, and other such things. You can also look at the activity of the fluorophore, the amount of intensity of the light that's being emitted from the fluorophore, and which wavelengths it's being emitted at. So this is a very useful tab which you'll also get to know. But for right now, we're going to go back to the Acquire tab. And as you can see, we default to the visible spectrum. And we're going to be selecting our laser lines here in a second and beginning our imaging. Remember that we have an acquisition mode tab, which should always be set for XYZ. We're always going to work in the XYZ mode. When the system first initializes, you will see the Z-Stack tab. We'll come back to that at the end of today's session. But for now, and by way of review, we'll go to the middle tab, which is the XY tab, and we're going to select the features that we need to run our experiment. Again, by way of review, you remember that we can select one of several different resolution formats. And this is the resolution of the digitizer. When the image is captured by the computer, it's stored in a digitizer in a certain format. A number of pixels across and number of pixels down in the XY digitizer. In this instance, the system defaults to 512 by 512. As we looked at last time, you can select a narrower window, and we'll do that by selecting 1024 by 512, which will give us a long, narrow window, which allows the refresh rate to be a little faster so that we can position our slide the way we want it, and we can minimize photo bleaching. The system also defaults to a speed of 400 Hertz. For now, we'll leave it at 400 Hertz, but as we increase in resolution, you'll see that we might want to increase in the speed of the system to capture images faster and minimize photo bleaching. We're going to discuss pinhole a little bit during this session, and we're also going to discuss zoom factor. I want to also point out these series of arrows, which are useful to direct the right monitor, not this monitor, but the right monitor image to a specific region of interest. So we'll cover that also a little bit during this session. We're also going to discuss line average, how to improve our images by doing averaging of each scanned line, and we will discuss frame average. In this instance, we will average each frame out a number of times according to the number we select, and that will decrease background noise. It will increase our signal to noise ratio and clean up our image. There are also two other tabs here for accumulate. You can accumulate the number of lines, and so if you have a very dim specimen, each line that you scan can become added to the next line depending on the number that you select here. The same goes for frame accumulation. Very rarely will you use these, but in some cases you might have a very dim return on your fluorescence, so you might want to accumulate all that information. Finally, there's a rotation bar here, and that allows you to rotate your image, your digitized image, on the screen. So we're going to begin. We'll come over here to Leica settings, and we will select FITC to start with. And so if we select FITC, the system will automatically turn on the appropriate laser, and you see that the 488 laser line is illuminated here on the spectrum, and it also gives us the emission curve. And so we know that we're going to excite at 488 nanometers, and FITC, fluorescein isothiocyanate, the fluorophore that we've selected for this experiment, will yield or will emit photons from about 520 up to almost 600. And so you see that our PMT, our photomultiplier tube, has automatically been activated. We see the gray bar underneath the slider indicating that we're going to be collecting photons from that area of the spectrum. And let's do one other thing. Let's close down our other slider bars and move them to the right. So we'll move these down out of the way. And let's extend the length of this PMT. And so you can see that we're now going to be collecting photons from a larger area underneath this curve. So now if we click on live on the lower left, we should get an image on our right screen. And as you can see, we now have an image over here on the right screen. As you can see, we have a live image on the screen now, but it's a little defocused. And so it's always important to make sure that my focus is properly set. So I'm refocusing now, and you can see that the finer lines are becoming nice and sharp, but I'm getting a little brightness here, which may be indicative of my laser power. Maybe my laser power is a little too high. And remember that I want to keep the laser power as low as possible to minimize photo bleaching. Now, in this particular specimen, we're only doing autofluorescence. There's no fluorophore been incubated or attached to this tissue. It's merely reacting to the laser light that is hitting it. And so in this sense, there's no cause for worry about photo bleaching. But when you're working with your live specimens and you've used a fluorophore, always be aware that whenever the laser is on, you're exciting that fluorophore and you're photo bleaching it. It's going to fail to give off energy after a period of time. I can always lower my laser. If you look over under the visible laser tab, I can lower the power of the laser by sliding this bar down a little bit, and you can see that instantly my image dims because I've lowered the laser power. So it's always a good idea to keep your laser power low if you can, but you might ask, well, how low? What is the benchmark? What should I use as a benchmark to determine my laser power? A good rule of thumb is to use what we call blue pixels and green pixels. What does that mean? Well, I'm going to click on this little lookup table icon on the left-hand side of the right screen. And you'll see now that my image has been converted to basically blue pixels and green pixels. And I select my gain and my offset. It's kind of like contrast and brightness by using these two knobs on the smart bar. And so I want to increase my gain until I have a few blue pixels at around 900 or 950. As you can see here, I have quite a few blue pixels, so I'm going to lower my smart gain down until I say only a few blue pixels. Now that's pretty low, which tells me that my laser could probably come down even a little bit more. A rule of thumb is to have the smart gain at around 900 to 950 volts. But for now, this will suffice. What about the offset? The offset allows me to lower the number of green pixels that I see on my image. And so I always want to have a negative offset. So I'm going to lower the offset down. Well, actually, you can see I'm not lowering it. I'm actually having to raise it a little bit, but it's still a negative number. And you'll see that my green pixels start to go away. And I want to find the spot where I have just a few green pixels. And the sensitivity of this knob is a little low right now. I can increase the sensitivity of it because it seems to be going from all green pixels to no green pixels. But a good rule of thumb is a smart offset, negative minus 1, negative minus 0.1, 0.2, or 0.3. So now I've finished using my lookup table. My gain and my offset are set approximately where they should be. So I'm going to click again on the lookup table twice. I go to grayscale and then back to my green color. And now you can see my image nicely illuminated, and my smart gain and my offset are set where I should have them. In order to improve our image quality for this specific application, I've increased the laser power a little bit. So let's once again look at our lookup table. We'll click on the lookup table. And now remember, we want to have a few blue pixels. So we'll increase our smart gain upwards of 900. I'm now at 925. And you can see I have a good amount of pixels here, but not too many. And again, my offset is set pretty much where I want it, right at the point where the green pixels go away. So I have a smart gain of 925, which is where I should be for my laser power, and a smart offset of minus 0.3. Now I can click through my lookup table again, and now I can see I have a pretty decent image. One important feature that you need to see related to the PMTs is the power of the PMTs to collect light information anywhere along this spectrum. I've turned off the FITC laser and the PMT, and now what I'm going to do is I'm going to turn on the UV laser. So you'll see a line generated down here around 405. So I'll turn that on. You see the 405 line being generated. And now I can activate this PMT, and now you see the gray area indicating that the PMT is going to select information from that region of the spectrum. I can narrow this PMT or I can lengthen it. Let's leave it narrow for a second. We'll click on live and look over here, and you can see not a lot of information on my top window. Again, I have two PMTs engaged. So the top window is PMT1, this is PMT2, and that's the composite. Let's turn off the composite image for a second. And so you see two windows. Now I'm going to come up to this window, and I'm going to increase the sensitivity of the PMT, and you will see illumination from our specimen over here. So let's concentrate on the left monitor for a second. I'm going to grab the PMT and stretch it out. And now you can see how much light enters this window from that region of the spectrum that we're just collecting from PMT number 1. So the photomultiplier tubes are very powerful in increasing the illumination of your image in areas of the spectrum that maybe you're not looking at based on what the manufacturer tells you about the fluorophore. So always be aware that you can activate any one of these laser lines and turn on the PMTs and find information in that area of the spectrum. So remember, just because a manufacturer gives you a suggested excitation line for their fluorophore or a suggested emission curve for their fluorophore, you have to think outside the box a little bit, and you can go find light information or photons in an area of the spectrum that maybe the manufacturer has not recommended. That's the power of these sliding photomultiplier tubes. So we'll look back at this, and you'll see again on the left screen, we have the photomultiplier tube stretched out in an area of the spectrum that's being excited by this 405 line. And then, of course, the Tritzy PMT is looking here. If we concentrate on the composite image on the right-hand side, you see a beautiful representation now of the light being emitted as a result of the excitation by the 405 line, and the light being emitted and collected as a result of the Tritzy line. So again, think outside the box. Use the tools that are available to you in this software so that you can stretch out into areas of the spectrum where you might not expect to see light, but it might actually be produced there.